Hi and welcome to Hydraterm's Lumber Kiln Simulator. In this series we'll explore how to use this tool to simulate complex lumber drying processes. In this first video I'll walk you through the interface and demonstrate a standard batch kiln simulation. You notice that the interface is organized into four main tabs. There's a Kiln Setup, Lumber Properties, Drying Process and Results tab. In the Kiln Setup tab we define the physical dimensions and the type of kiln, the lumber dimensions. In the Lumber Properties tab we define the species and the moisture content distribution. In the Drying Process tab we define the drying schedule, and in the Result tab we view all the graphs and visualizations connected to the simulation results. At the bottom we have the panel where we can save our setup, which is quite important because we're going to change a lot of values and it takes time to input all the values. Save your setup and then load it again when you start the program another time. Or share your setup file with colleagues. Then, we also have the Start Simulation button down here so you can start the simulation, pause it, resume it and stop it. So let's set up a batch kiln simulation. Of course we go with the default here. You will notice that we can insert reheat elements. So in that case, if this is an even number in total transverse stacks, then you can insert reheat elements. So you have to click on that and we'll render the kiln layout so you get a depiction of the reheat elements in the middle of the kiln. But we can just go without that for now. So you see there's 6 total transverse stacks, 1, 2, 3, 4, 5, 6 and only 1 longitudinal stack. Let's change that to 5 times 2. And then you see we get 5 stacks in that direction and 2 stacks in that direction. Oh, let's just keep it at 1 stack longitudinal. And then you can change how many packages there are per stack. But we'll keep it at 3. You can change the sticker thickness. The number of boards in the width is 15 at the moment. So if I would change that to 8 for instance, just to make a dramatic difference, then it would look like this. So now our packages are much narrower. But let's go back to 15 again. You can change the thickness of the boards of course and the standard deviation. So the stack height then is the distance from this bottom package support to the last layer of boards at the top. Then we can move on to the Lumber Properties tab. We choose species here. As you can see there's some hardwoods and some softwoods. And the species drying rates were calibrated to available publications or literature where a lot of the parameters were noted, like air velocity, density, kiln configuration, etc. You can choose then, let's say, Sitka spruce. You can adjust the species drying rate at this point. At this point, we accept it as it is. You don't know if you want to adjust it, so you would just leave it as it is. But later on, if you feel it's a bit too slow, but too fast, you can adjust it and increase or decrease the drying rate. Here you see the lumber properties, the moisture content, temperature and dry density, which is the dry weight divided by the dry volume. With the moisture content, you don't actually change that by entering the values. You change that by adjusting the limits. Adjust the lower and upper limits and adjust the peak value for the moisture content distribution. So let's say you have a lot of logs from mostly the bottom of the tree stems, therefore large diameter logs with a lot of heartwood. then you would expect a lower moisture content. So let's say you have a minimum of 30%, there won't be a lot of sapwood, so you set your maximum average board moisture content to quite a low value. And that's the average value of each board. And your peak would be to the left, or your distribution would be slanted to the left, like there, so your peak value would be more to the left towards the drier end. And if it was logs from the top of the tree stem, then you would have a higher moisture content and the peak would be more towards the right, and there would be less heartwood in your boards. So let's keep this distribution. You can see now, these values are updated when you change the values or change the scales here. Then we can set the temperatures, let's say it's springtime, or it's still quite cold outside, so let's set the lumber temperature to 5 degrees Celsius. Then you can change the density. If there's a lot of juvenile growth, you would have a lower density value. Preferably you would need to know which density values you have. The standard deviation is quite large, so I'll change that to 30. And then we are finished with the lumber properties. We can move on to the drying process. You can choose whether you want a time-based or a moisture content-based schedule. This graph depicts what you put into this drying schedule table at the top. You can see that at the moment it's time-based. And you can see the time values here in hours. If we change this, this becomes moisture content based. But still the flow is here from a higher moisture content on the left to a lower moisture content on the right. So let's just take it back to time. Then if you select ramp, which maybe would be the more common way to do it, the temperatures ramp up or down. And then we can choose control side. The entering control side means that we control the air temperature or the air coming into the stack. The exiting control side means we control the temperature of the air exiting the load. And the average is the average over the load. There's a tooltip that reminds you how this works. When you change this to, for instance, average, then you get 2 extra columns in the table, where you can actually, for each step, say what the maximum entering air temperatures should be. Because now we don't know the entering air temperature, so the entering air temperature has to be iteratively determined. So it can become quite a high value. And we want to limit that value to protect the lumber. Therefore you can put in a maximum value at each step here for both the dry bulb and the wet bulb depression, that is the difference between the dry bulb and the wet bulb temperature. But let's keep the control side as the entering air temperature for the time being. Now you'll see that we have 3 steps here. The first time step will always have to start from 0. And then at 4 hours, there's a change, and we'll be ramping up to those values. And then at 30 hours we have another value. So this is 0, 4, and 30 in the schedule. And the graph ends at 75 hours. And that's because we have got 75 hours as a default end time here. The kiln schedule will end either at 15% moisture content or at the target end time, whichever comes first. So remember that. So let's say we want to lengthen this to 100 hours. You can see that the graph axis maximum now has changed to 100 hours. Now we can add steps here. Let's say we want a heating up phase. Then we would change this step. We would say Edit. Let's say we think the kiln starts at about 20 degrees Celsius with a width of 18 degrees Celsius wet bulb temperature. Consequently, we get a warm-up phase here. Maybe then at this point we can have mild drying but at a full airspeed of 100%. And then let's say from 30 hours we want to reduce the airspeed a bit to 70% of full speed. And you can add steps. If you want to add a step in between those existing steps, you can say Add. Let's say at 25 hours. And yes, let's keep it at the same temperatures as the last step here. And we still want the fan speed at full speed. Let's say at 40 hours we want another step. So add a step, putting the value of 40 hours there. A little higher temperature maybe. And lower wet bulb temperature. Fan speed can still be a bit lower. We can set the maximum moisture content limit to 19. These are only for plotting some line in the moisture distribution result graph. They have no effect on the simulation itself. It's just for visualization in one of the graphs. And then we set the maximum air velocity at 5 meters per second for this. So for these two steps which have 70% fan speed would have an air velocity of 70% of 5 meters per second. Initial fan direction is forward. You can set different fan reversal intervals for different parts of your drying schedule. So this graph depicts all these settings that we set in the table and in these first two frames here. Then, if I click Enable Conditioning Phase, it will add on a conditioning phase but not in the graph. In the results graph you will see a conditioning phase as well. And then you can change how long the conditioning phase should be. It just takes the dry bulb temperature value from the last step in your table, but you can change it, and then it just calculates the equilibrium moisture content from those settings. Then you can set the fan speed for the conditioning step as well, and how often the fan should reverse. And now we've done the kiln setup, we've done the lumber properties, and we've done the drying process, so we can go to the Results tab. And here in the Results tab you can see everything is grayed out. There's nothing is presented at the moment because we haven't started a simulation yet. So here is a bunch of different graphs that will be shown. And then there's the individual board moisture content visualization. What it will do is to show one row of packages. So if we go back to the kiln setup, it will show one row of packages, like this. And the visualization will have a color scale connected to the moisture content and values for moisture content. And all that will be shown here at the bottom. So let's start the simulation. On every third time step in simulation, the graphs are updated. So we'll see how the simulation progresses. So let's pause the simulation. Now we are at 15 hours. We've gone through the warm-up stage, and the wet bulb depression is increasing, causing more aggressive drying. In the overall summary graph is a legend that shows the dry bulb set point, the wet bulb set point, and the average moisture content is dropping. The standard deviation and the temperature drop across the load is shown as well. In the visualization at the bottom we see each board end on in one row of packages. And so you both see an average moisture content value and a color associated with that value. Simultaneously, the surface stress evolution graph shows the stress at 1 mm depth. Positive values indicate tension and negative values indicate compression. The red line depicts average of the driest 10% of the boards. And the blue line depicts the average was the wettest 10% of the boards. Typically, softwoods have a tensional strength across the grain of 3 to 5 megapascals. You'll have to look that up for different species. But you should dry the wood in such a manner that the wood does not come close to the estimated tensional strength. There is a risk of surface checking when below that value because it's just an average value and there is a lot of variation in wood properties. So if it is a softwood, you would stay at quite low values like 1.5 megapascals, and you wouldn't want to go over that. And with hardwoods, it depends on the hardwood of course, but hardwoods often have a stress tolerance average value of up to 8 megapascals. So it could be quite high, and in that case you can maybe tolerate 2 to 2.5 megapascals to avoid surface checking. It is best to simulate a schedule that you know gives good results and see what surface tension levels are calculated and use that as a guide. The next graph is the horizontal temperature profile. This graph shows the air and lumber temperature profiles across the load. At the moment the fan is in reverse. So the temperature is high on the right-hand side. The air temperature is the red line and it's high on the right and drops toward the left as water is evaporated from the wood as the air passes over the lumber and exits on the leeward side. And the orange line is the lumber temperature, and you can see it's warmer than the air on the leeward side because the lumber was quite warm, so the lumber on the leeward side is still cooling down at this point in time. And the air temperature is a little below the lumber temperature. Moving on, the horizontal moisture content profile is just the average and standard deviation for each column of lumber through the load. So you'll see how that changes as the drying progresses. The moisture content distribution histogram still reflects the starting distribution we entered in the Lumber Properties tab, and here you see there's two limits that don't influence the simulation. The lines indicate the minimum and maximum moisture content within you want all your boards to fall. So we'll look at that again towards the end of the simulation. In the within board moisture content profiles you can see that the wettest boards are still well above the fiber saturation point from surface to surface in the board thickness. This axis is the thickness of the board. So 0 would be the center of a board in the thickness. So at the center of the board it is the wettest and then it gets drier towards the surface. The driest boards are already close or below the fiber saturation point. At the surfaces, they started getting a tensional stress because of the shrinkage. And then if you look at the within board stress profile you can also see that pattern. So right in the center there's a compressive stress and at the surface there's a tensional stress. And you can see there's no stress yet in the wettest boards because they're still quite wet from surface to surface. In hardwoods, or slow drying woods, the moisture content profiles generally will be more steep. So hardwoods would naturally be at higher risk for surface checks at higher average moisture contents. The simulator takes the drying rate of each species into account. Okay, so that was all the result graphs. Let's resume the simulation and let it go to its conclusion. You can see graphs update continuously as the drying progresses. You can see the load is starting to get dry at the edges. There is still a lot of wet boards in the middle of the load. Let's just pause there for a sec and look at the moisture content. You can see the edges here are starting to get drier than in the middle of the load. The moisture content distribution has moved down quite a lot. The goal is to get all the boards between these two lines. Let's resume and see what happens. Let's just pause here. You can see generally that the boards on the edges are drier. Also the top layer and the bottom layer of each package is quite dry. As you would expect in an actual lumber load. We've already reached the final moisture content here before we reached 50 hours. So the conditioning stage kicked in already. It's okay, but the wettest boards did have a fairly high tensional surface stress at a certain point. You can see the first and the last column of boards in the load are quite dry, so the boards on the side of the second package are more representative of the average moisture content. In an actual kiln, one would have to move the outer packages away and do measurements on the second stack to get a good idea of what the moisture content is. When looking at the final moisture content distribution, it's not good enough really, so we would have to make changes to our kiln schedule to get less variation and to get these wetter boards closer to the target moisture content. When looking at the within board moisture content profile, because we've had a conditioning phase, the driest boards actually got a higher moisture content at the surface than in the core, while our wettest boards were still drying in the conditioning phase, so the surface is still under tension, and that's also what we see in the within board stress profile. There are some tension at the surface of the wettest boards and compression at the surface of the driest boards. So that's an example of how a simulation of a batch kiln works and how to interpret the results. Thank you for your attention, and I hope you find the simulator useful.